In this lesson, we will be identifying transformations of functions. In each graph, the black line is the function f of x, and the gray line is the transformation of f of x. We will be determining the formula of the transformation in terms of f of x. So the first type of transformation we're going to look at is a vertical translation. When the k value is positive and added to the function, the graph will shift up. When the k value is negative and added to the function, the graph will shift down. So let's look at example 1. The black line is our f of x, and the gray line is the transformation of f of x. So notice this graph shifts up 3 units from the black line. So the gray line shifts up 3 from the black line, so we can say that our function for the transformation is f of x, taking that original function and adding 3. Let's look at example 2. Our dark line here is our function f of x. Notice the transformation shifts down 5 units. So in this function, we will write f of x minus 5, or you could say plus a negative 5. Let's look at example 3. Here, the dark line is our function f of x. The transformation shifts up 6 places, so we'll say f of x plus 6. Now let's look at some horizontal translations. When the k value is positive and added to the x values, the function of the graph will move to the left. Be very careful, positive numbers on the number line are not to the left. So you've got to think opposite there. Likewise, when the k value is negative and added to the x values of the function, the graph will move to the right. So let's look at that. Example 4. The gray line is going to shift to the right. Our function here is this dark black line, so that's our f of x. The gray graph shifts to the right, and it goes 3 places. So we're going to take our f of x, and since we're shifting our x value, we're going to add or subtract to that x value. If it's shifting to the right, it's going in the positive direction, but you will need to say minus 3 for that formula for the transformation. Let's look at example 5. Here we have our function f of x, the dark line. The graph shifts to the left 4 places. So again, we're going to add or subtract to the x value. Because it's going left 4, that is in the negative direction. However, you're going to need to use the opposite of that. So since it's going in the negative direction, we're going to say plus 4. And example 6. Here we have our function f of x. Notice it shifts to the right 5 places. So again, we'll say f of x, where we're adding or subtracting to the x value, not to the function, because it's our x values that are shifting left and right. Here we went to the right 5 places, so we will say minus, because we want to say opposite of the direction we're going, so minus 5. Always refer back to the fact that if k value is positive, it's going left. If the k value is negative, we're going right. Let's look at vertical stretches and compressions. Here, when the absolute value of the k value is greater than 1, so meaning when we look at this k value, not worrying about positive or negative, so the absolute value means it's always going to be the positive value. If it's greater than 1, the graph is going to be stretched vertically by that factor. So it's just going to stretch it out vertically when that value is greater than 1. When the absolute value of k is less than 1, meaning that value of k, again, not worrying about positive and negative, with absolute value it's always going to be positive. If it's less than 1, meaning a decimal value or a fraction value between 0 and 1, the graph is going to be compressed vertically by the factor of k. So let's write our functions for these transformations. Example 7. In order to do the vertical stretches and compressions, it's going to be helpful to identify a point on each graph with the same x values. So find a spot anywhere on the graph where you can look on the x-axis here and they fall on the same x values. So any points would work here. I've selected these two here. So at 5, 1 is our function f of x. And the transformation is at 5, 3. This will help you set up an equation and solve for the k value. So let's write an equation to solve for that k. If you'll remember, it's going to be k times your function that you originally start with. So let's set it up that way. Our k is what we're trying to solve for. The k is what we're trying to solve for, times, we know the y value, our function that it started at. So that needs to equal whatever the transformation was. So that equals the 3, which is where the y value is now. So if you solve this by dividing by 1, you find that k equals 3. So for each value of this function f of x, the transformation is multiplied by 3 to get our transformation. You can identify that in other points and multiply by 3, and it will stretch that graph as you see. So to write the formula, it'll just be 3 times f of x. Let's look at number 8. Here again, identify points anywhere where they have the same x value would be fine. I've identified this point here and this point here. So always start with your f of x function first. So the point on f of x is at 2, 4. I tend to pick numbers over here in the first quadrant if I can, so I'm dealing with positive, but you're welcome to pick any numbers that would fall on the graph where the x values are the same. The transformation of f of x, that point falls at 1, 2. So let's write our equation to be able to solve for k. So we're trying to find the k value when multiplied to our original function. So we started at 4. We're using that y value there, which I've done something wrong. I did not name my points correctly. 2, 4 for f of x. This should be 2, 1, because we should have had the same x values, 2, 1. So our y value there for the transformation is 1. So k times 4, that y value from f of x, is going to equal the y value of the transformation of f of x. So when you solve for k by dividing by 4, we get 1/4. So if you start at your f of x function, to do the transformation, every y value is multiplied by 1/4 in order to get the transformation. So we'll write 1/4 times f of x. Let's look at example 9. Let's identify 2 points. You could use any points along the graph. There's one here at 1, 1, as well as 1, 4. Or you can move along the graph, and here's one at 4, 2. That's our f of x function, the dark line. And the graph of the transformation is at 4, 1, 2, 3, 4, 5, 6, 7, 8, 4, 8. So again, set up an equation. You're going to start with your k value, which we don't know, so just use the variable k, times, we know our function, the y value is 2, so that's going to equal the transformation y value, which is 8. When we solve that, we can get our k value. When we divide by 2, we get that k equals 4. 8 divided by 2 is 4. So this is a vertical stretch by a factor of 4. So we'll say 4 times f of x. That means that every point along this graph of f of x was multiplied by 4 to get our new transformation graph. And finally, let's look at number 10. We'll identify the points here on f of x and our transformation of f of x. So we have 1, 2, 3, 4. So at 1, 4 for our f of x function. And for our transformation, it's at 1, 2. x1 and then y is 2. You do want to pick numbers that line up on the same x value so you can talk about what's happening from one function to the other. So writing the equation, we'll start with our k value, which we don't know, so use that variable k, times our 4 from our f of x function. That's going to equal the 2 from the transformation function. Solve this for k. 2 divided by 4, be very careful, that does not equal 2. 2 divided by 4 is 1/2. You can reduce this by dividing by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. So our k value is 1/2. And we can see that in the picture that the f of x function had a compression by half the size. Each y value is half the size in order to get our new graph of the transformation of f of x. So we'll write our formula as 1/2 f of x.